Well, good afternoon, students. This is Sharif sir. So we continue our topic. So yesterday we were discussing about rest and motion. Okay. So rest and motion. We recap briefly about what we discussed yesterday. So regarding rest, we were discussing that these two terms are once again relative terms. So we discussed what is meant by relative terms yesterday. Okay, regarding rest and motion, what are the keywords and what is the key role played by the words, that is frame of reference. Okay, and time. So based on these two, we define rest and motion. Now in the last we discussed one more concept called as path. One more concept called as path yesterday. Okay. So what is path? It is the line joining the different positions of the object during its journey. During its journey is called path. Okay, path of the object. So path of the object. Right, dear students. Now let us see this once again. So we continue. So while discussing the line joining the different positions of the object during its journey is called path of the object. Now based on this path, if it is straight, we discussed that it was rectilinear motion. If it is curved, we said that it was curvilinear motion. And then if it is circular, we said that it is a circular motion. Or else if it is a pendulum like thing, that means a weight attached to a string and once again tied to a rigid support. So this, if it is moving like this, so such a motion so friends, so these are the different types of that. This was harmonic motion, right? So this we have discussed today. Now let us see little bit in detail discussion of this part. So students, the line joining the different positions of the object during its journey is called path of the object. Okay, now you look at this. Suppose The object was initially here, then here, then here, then here, and then finally here. So this is the initial position, and this is the final position. Now the line joining the different positions of the object during its journey is called as part of the object, as simple as it is. Right. So let us join all the positions now. Now we get something like this. So this is the initial point or the starting point. Okay. So initial point of the journey of the object, and this is the final point. Final point. So initial point and final point. Now very simple as it is. Okay. Now you can measure the length of this path. The length of this path right from here up to here. Yes or no? Okay. So we can measure. That means how do you measure the length of the curved path? We can measure. Suppose for example, if we consider this one here now. Okay, we can take a thread or something, and then we keep the thread along the path. Then take the thread, just to keep it on a scale or tape or whatever it is, and that is the distance. Okay, so this is the new term. Again, once again, distance. Okay, that becomes the distance traveled by the object, which is our present discussion. Okay, distance and displacement. We go to the displacement later on. Now another quantity called as displacement. Displacement. So displacement we define as the directed line segment from the initial position to the final position of the object. The directed line segment from the initial position to the final position of the object during its journey, of course, is called as displacement. Okay, we discuss this one afterwards, little bit. Okay, now here let us see about distance now. What is distance? So the length of the path traveled by the object during its journey is called distance. The what is distance? Length of the path. Length of the path traveled by the object. Traveled by the object. Object during its journey. During its journey is called distance. Distance. So this is the definition of distance. This is the definition of distance. As simple as it is. So look at the definition once again. Here, that's what we discussed about path in the beginning. Okay. So if you see, it need not be like this only every time. Okay, it need not be like this only. That could be something like this. Like this. Okay. So this is the initial position or initial point. Okay, and this is the final position of the object during the journey. Anyway, it is curved. So whatever it is, we can measure the length, we can measure the distance. Right. So length of the path traveled by the object during its journey is called a distance traveled by the object, or simply distance. Right. So now this distance, okay, it is having, what is the unit we measure? What is the SI unit? It is meter. SI unit is meter. Okay, we have similarly CGS units and FPS units that you know very well, right? Okay, CGS unit we measure in centimeter, FPS unit we measure in foot. Okay, what is FPS? Foot pound second. And what is CGS? Meter gram second. What is MKS? Meter kilogram second. What is SI? Meter. Okay. Now we follow. This is the SI unit. Okay. So this is the SI unit of distance. Okay. Now we say that this is a scalar physical quantity. Okay. Okay. This is a vector. This is a vector. So what is vector? What is scalar? Let us see now. Now distance. Okay, distance is scalar. Distance is scalar. Scalar physical quantity. Scalar physical quantity. What is the scalar physical quantity, vector physical quantity? What is physical quantity first of all? Physical quantity is that which can be measurable. Anything which is measurable is called as a physical quantity. Anything which is measurable is called as a physical quantity. So among physical quantity, as per one type of classification, we have scalars and vectors. Scalars and vectors. Let us see this now. So what is a scalar and what is a vector? So first we will discuss what is a scalar physical quantity, what is a vector physical quantity, because we are studying about distance and distance is a scalar physical quantity. Distance is a scalar physical quantity. So now distance length of the path traveled by the object. So this is the definition. Then its SI unit is meter. So it is meter. Then again, it is a scalar physical quantity. Scalar physical quantity. Right. So it's a scalar physical quantity. So let us see what is a scalar physical quantity. So what is a scalar? So simply we say scalar. Every time we don't speak physical quantity because it is understood. Okay. So what is a scalar now? Okay. Any physical quantity which has magnitude but no direction is called as a scalar physical quantity. Simply scalar. So once again, any physical quantity which has magnitude but no direction is called as a scalar. Right. Any physical quantity which has magnitude but no direction is known as a scalar. Is known as a scalar. Right. So what is this physical quantity which has magnitude? What is this magnitude once again? What is this magnitude once again? Suppose, let us see a few examples. Suppose what is my weight? My weight is 70 kg. 70 kg. Suppose I need milk of 2 liter. Okay. Okay. 2 liter of milk. 2 liter of milk. Suppose what is the current flowing into the fan now? Suppose it is 3 ampere. 3 ampere or in otherwise 3 ampere. Okay, 3 ampere of current. What is the light falling here? Candela. The intensity of light falling in this room. Suppose. Okay, some 100 candela. 100 candela. Okay. So some more examples. Right. So what is the temperature right now? What is the temperature right now outside? Suppose roughly around maybe 42 degrees centigrade. Maybe 42 degree centigrade. right? So, for example, so how many molecules are there in this total marker pen? Suppose, okay, so that is some 3 into 6.023 into 10 power 23 moles are in a chart piece. Okay. So similarly, look at all these things. We have here 42 degrees centigrade, 70 kilogram. Or suppose what is the time now? Time now somewhere 2 hours 30 minutes. Not just okay. 3 seconds. 3 seconds. Okay. 3 seconds. Then so look at all these things. Look at all these things. We have 42 degrees centigrade. We are speaking about temperature. 70 kg 3 second. 3 second. As per the rules of SI units, we should not speak any unit in plural. One of the rule, right? 42 degrees centigrade. No, 42 degrees centigrade. Then 70 kgs. Kgs is wrong. Kg, kgs wrong. Kg. So we say 3 second, 3 seconds wrong, 3 second, right? Similarly, 3 ampere, not amperes. Okay, no unit should be spoken in plural, just one rule. Okay, okay, that is a different discussion. We'll discuss it later. Right now, okay. So 3 ampere of current, then 2 liter milk or 2 liter water, something, and these many number of moles in a marker pen. So these plastic molecules or plastic atoms. Okay, then how much of light is, what is that? Intensity of light falling from the sun in this room of this much area, that is something around, okay, 100. So we are speaking about here, okay, look carefully. We are speaking about a number and a unit. 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 Another number and a unit. Number and a unit. Number and a unit. So what is magnitude? What is the meaning of magnitude? If we speak a physical quantity in its number along with the number along with the unit. Okay, number along with the unit is called as magnitude of that particular physical quantity. To be very simple, it's the simplest definition for magnitude. Okay, complication is there that you study in your later classes. Okay, right. So here, just if we have to understand it in the simplest, as simple as it is, then what do we say about magnitude is, it is nothing but the combination of a number and its unit, number and its unit, number and its unit, number unit, number and. So I think now you would have got a very clear idea about what is the magnitude of a physical quantity. Now you look at one more discussion. Suppose I said that my weight is 70 kg. If I say my weight is 70 kg due north or 70 kg due east, 70 kg northeast, are you listening? So just what is my weight? 70 kg. Answer is over, sufficient. It is meaningful. Suppose if I speak 70 kg due north, the person will look at me up and down like this. That means whether he is gone mad or what. Means for expressing certain physical quantities, what are they? Scalars. So scalar do not require direction. Do not require direction. Okay, scalar physical quantity do not require direction. So if we speak it without direction also, it is very meaningful and it conveys the complete sense here. Right. So you go to a vegetable merchant. Suppose if you say I need 3 kilo tomatoes due southwest. What is this? 3 kilo tomatoes is sufficient. Give me 3 kilo tomatoes due southwest means that fellow will look at you like this. From where this fellow came? something. Okay, so 3 ampere. Similarly, all these things. So that means scalar do not need direction. That's why in the definition, what they are saying, any physical quantity which has magnitude but no direction is known as a scalar. Is known as a scalar. So here, if you have this doubt about this magnitude, so nothing but the combination of number and unit. Number and unit. So it is clear for you now. Now let us see what are these physical quantities. So like this we have a broad classification. So we are saying this as scalar. Okay, scalar physical quantity. Now again, one another division of physical quantities we have, that is fundamental physical quantities. Fundamental physical quantities. And then derived physical quantities. Just I am reminding you. Derived physical quantities. What are fundamental physical quantities? These are all the same things. So we can put the examples of scalars here. So what are the fundamental physical quantities? Let us say length, mass, time, thermodynamic temperature, strength of electric current, luminous intensity, and the amount of substance. Okay, I'll present it here. Just go through. Okay, length, mass, time, strength of current, strength of electric current, thermodynamic, temperature, then amount of substance, then finally intensity, luminous intensity. So these are the fundamental physical quantities. Okay. So totally 1, 2, 3, 4, 5, 6, and 7. 7 fundamental physical quantities. So what are these fundamental physical quantities? By definition, means these are the physical quantities which do not depend on other physical quantity for their existence. Suppose if I need what is the length or breadth of this table here. So I take a tape, just I measure it. Finish. No direction. That means this length is not depending. That means to find the length, I need not bother about its temperature or amount of substance present in whatever. Okay. So length means I take a tape and measure this. That's all. Finish. This one table, length of this table here. Something. Okay. So any physical quantity among this do not depend on other physical quantity for its existence. Which means since the formation of this universe, means since the formation of the earth or the solar system or our Milky Way or whatever it is. Okay, whether you go anywhere in the universe, if there is a mass, okay, if there is mass, or you go to a planet or something, whatever it is, okay, so these things will be present there. Initially we did not know about these things. We knew only about length, mass and time in the earlier days. So later on these were present, but we don't know. Okay, human being. Okay, in the process of evolution, you know that one very well. So evolution. Okay, he was understanding the nature. What is science actually? What is science? We are discussing physical science, right? So basically, as simple as to say, what is science? Understanding the nature. It looks so simple, but it is very complicated. Understanding the nature. Suppose, let us take an example. Leaves are green in color. So why leaves are green in color? Fish. Because this is one of the because we see many plants in the nature. Okay. Suppose another example. During rainfall, sometimes thunderstorms occur, lightnings occur. Okay, lightning. So one cloud is rubbing with the another. Light as well as sound are produced. That light we call it as lighting, and the sound we call it as thunderstorm. Thunderstorm. Okay, so this we understood now. We are able to understand now. But earlier, people do not know, did not know what is all these things. Okay, that clouds carry charges, and once they rub one cloud with another cloud, that electricity is generated and it is reaching the earth. Okay, so all such things as the people did not know. So that's why these things, even if they are present, even if they were present earlier, even if they were present earlier, human being could not know. But during the evolution, human being is started understanding all the things what is happening around him. Suppose, for example, photosynthesis. Why the leaves are green color? Because during photosynthesis they produce oxygen. Okay, they release oxygen finally. And due to the presence of a pigment called chlorophyll, the leaves are whatever it is, green color. Okay, stem, whatever it is. Okay, so that you learn in biology. So now let us okay, that is what is nature. Why the clouds are forming, why the rainfall, and why these earthquakes, tsunamis. So these are all nature. Okay, and what is the distance of moon from the earth? What is the distance of sun from the? These are all nature. Okay, so in which galaxy we are present? So everything is coming under science. So human being, as the time is passing, okay, so this is the powerful organ which is nothing but the brain which is present in our skull. Okay, so started questioning why, how, why and how. Okay, so in that these are found. So finally, see if you see this primitive, that means the units we have FPS. FPS. So foot pound second. People used to measure length by one unit called as foot. 1 foot, 2 foot, 3 foot. Okay. So what is the length of this room? Around 14 feet. Even now, people used to express. People, you would have seen people expressing the length in foot or feet. Okay, what is the area? So and so square feet. So and so square feet. So what is the square feet? Even now also people are using a few kinds of units which are not SI units. Which are not SI units, of course. Now, but coming to SI units, these are the SI units. Okay, we'll discuss that one now. Okay. So finally, what is science? Understanding the nature is science. That's all. So in that process, okay. So we have all these things as fundamental physical quantities. Suppose if you go to NJS in one country, that means in one area, that means Britain or United Kingdom or Europe, people used to follow foot pound second. In some other areas, meter kilogram second. So these are the two familiar. Now, as the time passed, so these are the other physical quantities known by man. Known by man. So what are these? So strength of electric current. So simply current. Then thermodynamic temperature or simply temperature. Again, amount of substance. That means how many moles or how many atoms, how many molecules are present in so and so particle. Okay, whether it is a chalk piece or some stone, small stone, or some other thing. Okay, how many moles or how many atoms, how many molecules. So that is expressed in moles. Now coming to the luminance, finally luminous intensity. That is intensity of light. So even we can measure the intensity of anything which is measurable is a physical quantity. So among that one kind of classification is fundamental physical quantity and derived physical quantity. These physical quantities do not depend on other physical quantities. That means if you want to know the electric current, suppose what is the current passing in a square. Okay, we need not know about the length, mass, time of this room and all. Or length of the wire, mass of the wire, not necessary. Okay, so again similarly, thermodynamic temperature. So if I want to check my temperature of my body, just I take a thermometer and then I keep it in my mouth. So for that, my weight and height is not necessary, no. My weight and height is not necessary. That is length, not necessary. That means it is independent unit. Okay, similarly, amount of substance, similarly luminous intensity. So let us see the units for all these things. So length we have in SI. Okay, SI units. Right? Units. So length is in meter. Meter. So symbol M. Then mass kilogram, kilogram, and that is kg. And the time second, second. Time is second. Just S. Then strength of electric current, ampere, ampere. So that is A, ampere. And then thermodynamic temperature, Kelvin, Kelvin. So simply capital K. Then amount of substance, that is mole. Mole. Symbol is mole. Just one E is removed. Then luminous intensity, candela. Candela. So CD. This is the unit. Full spelling. This is the symbol. This is the symbol. Okay. Symbol. Right. So these are all scalars. So why I told these are all scalars. Example for scalar, you can quote any of this. Any of this. Okay, not only this, some others also. Now here, see, to tell length, direction not necessary, to tell mass, direction not necessary, to tell time, direction not necessary, similarly, all this. So look at here, one small key point what you have to observe here. See, everywhere, when I was writing the spelling, I started with a lower order alphabet. Lower order alphabet are simply small letter. What is that? Small letter. So, why small letter? That is the rule. So why small letter? That is one of the rule. Like what I have told earlier. No plural. No plural. While speaking any unit. Now, while writing the full spelling, of any unit in physics, while writing the full spelling of any unit in physics, full spelling. When you are writing the full spelling, you should start with a small letter or alphabet of lowercase. Lowercase. That is Kelvin K, mole, candela C, small c, small c. Okay, that is the rule. But when you write the symbol, you can write meter, and then kilogram. First one is capital, and then second. Okay, you can write this one like this. You can write second capital. Okay, so kilogram. Then ampere, capital. So here mole. Okay, this is small. Then here you can write like this. First letter. First one is mole. Okay, then candela. This is first one is capital C, small. Capital C and small. Okay. So this is how we represent the fundamental physical quantities. Then they SI units. Then they symbols. They symbol. And then some more we have. Suppose you want to write what is the another name? Some other scientist name. Okay, Newton force. We express force in Newton. So how do you write that? Newton. If you are writing Newton as a unit, then if you are wishing, if you wish to write the full spelling, you should write Newton. So you may get it out as per the English grammar. Our English teachers taught us not to write name with a small alphabet. Of course, who is saying it is a name? It is a unit. It is not the name. Of course, it is conveying the name of Newton scientist, but you are writing the unit now. It is not the name, of course. Of course, in the name of the scientist, but you are writing that name as a unit. As a unit. That's why you start with a small letter. If you represent it in a pressure? Pascal. Pascal is the name of the scientist. Okay. So Pascal, if you are writing, see, Pascal. But if you are representing it in a simile, so Pascal, PA, like this you represent the symbol. Okay. So this is one another rule while writing the SI units. Okay. Of course, you should not keep like dots or full stop after writing a unit. For example, suppose 70 kg and 70 kg I should know. So 70 kg dot wrong. Just 70 kg should leave. So that means no grammar mark. That means full stop, comma, semicolon, inverted, nothing. Okay. So you represent the unit. That's all. Finish. No full stop. So that is another rule. So like that we have few rules. Okay. Did you understand this one now? Okay. So that is what is a scalar physical quantity. Any physical quantity which has magnitude but no direction is known as scalar. Is known as scalar. Now, what is scalar example? Example for scalars. I have told all the fundamental physical quantity. That means based on one kind of classification, we have all this list. And example for scalar, you can quote any of these. Okay, right. Then what is a derived physical quantity? What is a derived physical quantity? Okay, let us see about this now. So a derived physical quantity means the physical quantity which is derived from one or more physical quantities. For example, area. For example, we need to find the area of this marker board. We measure the length and we measure the okay. Or suppose if I need to find the density of a liquid. Okay, density area L into V. Then density mass per unit volume is called as the density of the substance. So in density, if you don't know volume, you can't find proceed or you can't find the density of the substance. If you don't know mass also, you can't find the density of a substance. That means this physical quantity density is interdependent. That means it is depending on two other physical quantities called as one is mass and another one is volume. Okay, some more examples. So derived physical quantities we will discuss now. So derived physical quantities in detail. Okay. Okay. Look here. Derived physical quantity. See here, this word derived itself is saying some meaning with it because it is being derived from some other thing. You take the meaning here, derived. You would have come across derivations in mathematics. You need some data. So from the data, you derive some other data. Okay. So derive so and so. Okay. So derive that the sum of three angles in a triangle is 180 degree. So you get the derivation. For that you need some data. So here also this derived physical quantity itself means that it is depending on some other physical quantities for its existence. But you look at the fundamental physical quantities, they are not depending on any other physical quantity for their existence. Now look at this example. Okay, we have area means we need product of length and breadth. Suppose volume we have length into breadth into height of an object, of course, regular object. Then force. Last year we have studied force. The definition: mass into acceleration. Suppose energy or simply what to do? Okay, kinetic energy. Energy is equal to half m v square. Where is velocity? Okay, if you are not familiar with the velocity, okay, we'll discuss that one later. potential energy, potential energy, mass into acceleration into gravity into height, mgh. Okay, these are all the okay. Density is equal to mass per unit volume, and then power work done in unit time, work done in unit time, acceleration, rate of change of velocity means velocity by time, velocity by time, etc. and so on. So on. Many examples you can consider. Now look at this one by one. Okay. So we have derived. See, we derive area by multiplying length and breadth. We derive volume by multiplying length, breadth, and height. We derive force by multiplying mass with acceleration. We derive kinetic energy, okay, by multiplying half with the mass and the square of volume, square of velocity of the substance. Then we derive potential energy by multiplying mass, acceleration due to gravity, height at a particular substance is there. Suppose the object, if it is at a particular height from the ground, then it is said to be possess potential energy. Potential energy or simply gravitational potential energy also we can say. Then coming to another thing called density, mass per unit volume means we can derive density or we know the density, okay, only when we know both mass and volume of a regular object. Means if we don't have this data, we cannot get the density. If we don't have this data, we cannot find the density. Similarly, power of a person or an engine or whatever it is. Okay, power of vehicle. Suppose this bikes and cars would have seen great horsepower or power. Okay, 30 bhp, 40 bhp, 10 bhp, something. Okay, work done in unit time. Work done in unit time we express in power watt. Okay, acceleration, velocity per time. Okay, velocity divided by time. So these are the examples, a few examples for the derived physical quantity. So why we discuss this one? We got with the scalar. For scalar example, we have discussed that the physical quantity which has magnitude only but no direction is called as a scalar. Examples, fundamental physical quantity. So as we discussed fundamental physical quantities, we discussed derived physical quantities also. Now let us go to the next topic. Now let us discuss about the motion. So to find this, uniform motion and non-uniform motion. Non-uniform motion. So if an object is moving equal distances in equal intervals of time, Right, students? I will see these two definitions or simply concepts. Okay. Now look at here. Uniform motion. Equal distances in equal intervals of time is a, that means if an object moves. If an object moves, moves equal distances in equal intervals of time. If an object moves equal distances in equal intervals of time, we say that the object is in uniform motion. For example, you see, suppose we represent it in the form of a graph, right? So this is 0, and then we have 1, 1, 1. This is time in seconds, time in seconds, and this is distance, distance in meter, distance in meter. Suppose 1 second. Okay, so 5 meters, 2 seconds, 3 seconds, this, 5. See, 1 second, 5 meters, 2 seconds, 10 meters, and 3 seconds, 15 meters. 15 meters. Okay. Okay. Now the object is traveling similarly. We can continue. Okay. The object is traveling equal distances in equal interval of time. Suppose see here 1 second 5 meters. 5 meters. Next second is 2 seconds. This is 10 meter. Meter. So 2 seconds 10 meters. Then divided by 2. 5 meter per second. So 5 meter per second. Then 15 3. That is every second it is traveling 5 meters. 5 meters. Every second it is traveling 5 meters. Means 5 meters is the speed with which it is traveling every second. Means equal distances in equal intervals of time. 1 second 5, another second another 5, another second another 5. So on. So like that, if it is such a thing or such a scenario, you call it as uniform motion. But you see, suppose I take another example here. Okay, time. So time in seconds and distance in meter. Distance in meter. Suppose 1 second an object has traveled 2 meters. Another second, okay, 5 meter. That means in 2 seconds, 5 meters. So if you divide this, you will get the value. Then 3 seconds, okay, in third second, some 16 meter, 16 meter, so on. So look at this now. In 1 second, 2 meter, okay, 2 meter per second. In 2 seconds, 5 meter. So 5 by 2 is 2.5. Okay, this is 2, this is 2.5. What is the speed? 2.5 meter. Then again, 16 by 3. Okay, so this is non-uniform. That means it is not covering same distances in equal intervals of time or unequal intervals of time also no problem. Okay, so such a scenario, we say that it is non-uniform motion. Uniform motion and non-uniform motion. Now let us come to the next topic, that is speed. Okay. So the definition of speed we have. Just if we say speed, it will be not so appropriate because there is nothing like simply speed. Okay, right. So, what is speed? Let us see now. How do you define speed of an object?